All right, welcome everybody. So today we're going to be discussing differential rate laws, or just rate laws. And so by the end of today, you guys should be able to determine the rate law and the rate constant from experimental data. So first off, what is a rate law? So a rate law is an expression, aka equation, showing how the rate depends on the concentration of the reactants. So all rate laws look like this. The rate, which again is going to be in units of molarity or concentration, however the concentration is measured, divided by time. So it's going to be concentration over time for the unit of rate. It's equal to K times the concentration held to some power. So let's talk about this equation real quick. Again, K right here is going to be the rate constant. So let's fill that in. This right here in the brackets, that's going to be our concentration, which most of the time is going to be in units of molarity. And then N, this exponent right here, is going to be called an order, okay? We have to use experimental data to determine the rate constant and the order. Now, unlike a mole ratio or most of the other things we do in chemistry, our rate law cannot be determined by looking at the balanced chemical equation. Instead, the rate law can only be determined by looking at concentration data over time. So the question is, how can the rate law be determined from initial rate data? So if we're given rate data, how can we figure out this rate law? So the method of initial rates is used to derive a differential rate law from initial rate data. So if we're given data regarding the very beginning of the experiment, the speed of the reaction at the very beginning of the experiment, we can derive this differential rate law. And again, that's this right here. So a differential rate law looks like this. I have my rate set equal to my rate constant times the concentration held to some order, some exponent. So let's go ahead and take a look at how this works. So we're given this data here. It says given the reaction A plus B yields AB, so a synthesis reaction, and we have this data here, we need to figure out our rate law. So we start by looking at and comparing two experiments in which A changes, but B remains constant. We want to make sure that we pick two experiments where A is changing, so I can look at how A affects the rate, but not at how B affects the rate. We want B to be held constant. When you're doing stuff in science, it's really important that you only have one independent variable at a time. We just want one thing to change so that we can look at its effect on our dependent variable, the rate. We don't want both A and B to change at the same time, because then we can't attribute the effect of either one to the change in rate. So we're just going to look at how A changes and how that affects the rate. We're going to try to look at two experiments in which A changes and B remains the same. Now if we look at that rate data, we can see that in experiment 1 and 2, A is the same, so we're not going to compare experiments 1 and 2. We could compare experiments 1 and 3 or experiments 2 and 3, because in 1 and 3 and 2 and 3, the first one is 0.10 and experiment 3 is 0.2, the concentration. For the concentration of B, if we look at it, the concentration in experiments 1 and 3 is both 0.10. So it's the same in experiments 1 and 3 for the concentration of B. So that means we're going to look here at experiments 1 and 3, where A doubles and B remains constant. So experiments 1 and 3 in this case are going to be the ones that we look at because A is changing and B remains constant. So the way that it works is our rate is equal to some change, or our change in rate is equal to some change in the concentration of A held to a power. So let's think about this for a second. We need to look at this as the change as a sort of a factor, right? What was the factor of change? If we look at the rate, and again, we're comparing experiments 1 and 3. In experiment 1, the rate was 0.04. In experiment 3, it was 0.16. So my factor of change, if I think about it, from here to here, it changed by a factor of 4. So we're not adding or subtracting here. What we're looking is to see what the factor of change is. So we want to know how many times was it multiplied from one experiment to the other. And in this case, from experiment 1 to experiment 3, this was multiplied by 4. So our rate of change is 4 because the rate increased by a factor of 4. We're going to do that same thing here. If I compare the two concentrations of A in experiments 1 and 3, from experiment from experiment 1 to experiment 3, the concentration of A doubled. So it changed by a factor of 2. So my rate of change of A is 2. Now that's held to some power. So really what we're trying to do in this case is use those factors of change to determine the exponent for this rate law. And so 4 equals 2 to the power of x. We can think about what x is going to be for a second. X has to be 2. And so x equals 2, which means that this experiment is second order with respect to A. So when we write our rate law, the concentration of A is going to be held to the power of 2. Our order with respect to A is 2. So it's second order. Then we have to do kind of the same thing for B. We have to figure out where B changes, but A remains constant, so that we can attribute any changes in the rate to changes in the concentration of B. And if we look at that, I'm going to go back up here to the data. If we look at it, we can see that in experiment 2, B was 0.2. So we can either compare experiments 2 and 3 or experiments 1 and 2. If we look at the concentration of A, it's held constant in experiments 1 and 2. And so that means that since this isn't changing, it's not affecting the rate. It's the change in B that's affecting the rate here. We can see that from experiment 1 to experiment 2, our concentration of B doubles. So there's a factor of change of 2. We can see that here, it's the same. So the factor of change here is 1. It's exactly the same number. So let's set that up mathematically and see what happens. So our rate was 1. Our factor of change in the concentration of B was 2 because it doubled, and that's going to be held to some exponent. So now we have to kind of think about what that exponent is going to be. And if y were 1, then the factor of change in my rate would be 2. However, it's 1. So there's only one thing that could cause, one exponent that could cause 2 to end up being 1, and that's 0. So y equals 0, which means that this is 0 order with respect to y. So when we write the rate law, we can put b to the power of 0, or we can leave it out entirely because it's equal to 1, and mathematically, if you have an equation, 1 does nothing. 1 is useless in an equation unless you're adding or subtracting, but here we're multiplying everything. And so having 1 in a multiplication equation is sort of worthless. So we can just take it out entirely, and we can write our rate law like this. Rate equals the concentration of A held to the second power. And that's it. Also, we'll need a rate constant right there. So don't forget the rate constant in your rate law. Let me go ahead and do this. We can also find K. We can actually find that number. And so the way that we find K is we can pick any experiment, and I usually pick experiment 1, but you can pick any of the experiments and use the data from that experiment. So I'm going to pick experiment 1, and I'm actually going to plug these values in. So the concentration of A is 0.10, and my rate is 0.04. So I can plug those values in. My rate was 0.04. It's equal to K times my concentration, which was 0.1, held to the second power. So let me go ahead and multiply that out. So 0.1 times 0.1 is going to be 0.01. So 0.040 is equal to K times 0.01. Once I squared 0.10, that's what I got. And so K times 0.01 is going to give me 0.04. Well, what does K have to be? If we divide both sides by 0.01, we end up with 4. So 4 is going to be our value for the rate constant in this case. Another thing to consider are units. So this is where things get a little tricky. So we need to think about the units. The units on K are dependent upon the order. We know that the rate is equal to, in this case, our concentration was molarity, and our time was, our rate was in molarity per second. So rate is molarity over seconds is equal to sum K times molarity squared, because we took a molarity and we squared it right here. We need to think about what unit K is going to be in order to end up with molarity over seconds. So what could we multiply times molarity squared to end up with just a single molarity on top and seconds on the bottom? K could be equal to, I'm going to put it over here, 1 over molarity times seconds. Why? Because that is going to cancel out one of the molarities on top and leave us with seconds on the bottom, so that our end unit for rate is a single molarity over seconds. So our value for K is going to be 4, and the unit for that rate constant is going to be 1 over molarity times seconds. And again, that could be different if you have a different order for the reaction. Okay, so then how can a differential rate law be determined if a reactant concentration is not held constant? So what if both of them happen to change throughout the course of the reaction? So what we have to do here is we have to be careful, and we have to find 2 experiments in which at least one of the reactants is held constant. Okay? And so A is held constant. If we look at this data, A is held constant in experiments 2 and 3. So in experiments 2 and 3, we can at least use the same process as before to figure out the factor of change on B and the factor of change on the rate to determine the order of B. So that's what we're going to do. So if I look at this experiment, from experiment 2 to experiment 3, the concentration of B went from 0.4 to 0.8, so that's a factor of change of 2. It doubled. Let me think about how the rate changed. It went from 3,600 to 14,400. So what I can do is I can actually divide to figure out what that factor is. So 14,400 divided by 3,600. That's a factor of change of 4. So the rate changed by a factor of 4, the concentration changed by a factor of 2. So again, we can set this up. Our factor of change in the rate is equal to the factor of change in the concentration of, in this case, B, held to some power. We know that the factor of change in the rate was 4. We know that the factor of change for the concentration of B was 2. So we just have to determine the order. And 2 to the power of 2 is going to give us 4. So X is going to be the order of reactant B, and it's going to be second order with respect to B. That exponent is 2. Now, the issue is that in none of the experiments was the concentration of B held constant. So unfortunately, the scientists didn't follow the rule, and they didn't have one single independent variable. In these experiments, a lot of them had 2 things changing. So we're going to have to use actually the order that we've already determined in order to figure out the order of A. So we're going to determine the order of the other reactant by examining 2 experiments in which A changes, and include the order of reactant B in the calculation of the rate law. Okay, so let's go ahead and we can just kind of look at it before I flip the page. Let's do that. I think it's easy to look at experiments 1 and 2 just because they're right there. If we look at it, A changed from a concentration of 0.1 molar to a concentration of 0.3 molar. So that is a factor of 3. Now, in the same time period, in the same 2 experiments, the concentration of B doubled, and our rate changed quite a bit. So our rate went from 300 to 3,600. So again, to figure out that factor, we can take 3,600 and divide it by 300, and that's going to be a factor of 12. So we know that A changed by a factor of 3, B changed by a factor of 2, and the rate changed by a factor of 12. So let's think about our rate law for a second. Remember that our rate law is equal to the factor of change in A held to some exponent, which we don't know yet, multiplied by the factor of change in B. And we already know the order on this one because we've already determined it. It's the order of 2. So that exponent is 2. So now let's fill that in. We know that the factor of change for the rate in this, when we compared experiments 1 and 2, was 12. We know that A changed by a factor of 3. And we know that B changed by a factor of 2. And we know that that 2 is going to be held to the second power. So we end up with 12 is equal to 3 held to some power times 4. You can divide both sides by 4. We end up with 3 is equal to 3 to the power of something. And the only thing that we could put there so that the numbers on both sides are the same is 1. So y equals 1. And so that means that A is first order. It's going to have an exponent of 1, which honestly, again, in math, when we're multiplying and using exponents, 1 isn't that handy. So we could actually just leave the exponent off of there. Okay. And again, we can figure out the value of the rate constant. So using that differential rate law that we just determined from the data. And again, it can only be determined from data. It cannot be determined by looking at the balanced chemical equation. If we look back at the balanced chemical equation, let's do this real quick. There was actually a coefficient of 2 in front of A. But we know that this experiment is first order with respect to A and second order with respect to B. So those coefficients did nothing to help us figure out the differential rate law for this experiment. What did help us was analyzing the data to see the factors of change in the concentrations of the reactants and in the rate. So again, we're going to use that differential rate law that we've determined from data and plug in the data from any one of the experiments to actually solve for K. So if we look at it, I just always use experiment 1 because it's right there. The concentration of A is 0.10. Now we know that's going to be held to the first power because in our rate law this is first order. I could put the 1 as the exponent or leave it off because mathematically that's the same. That gets multiplied by the concentration of B, which we know is going to be second order. So in experiment 1, the concentration of B was 0.2, and it's held to the second power. Again, we're multiplying that times a rate constant and setting it equal to the rate, which in the first experiment was 300. So now we just have to do some algebra to solve for K, and then we can think about the units that'll be associated with K. If I take 0.2 and square it, it should be 0.04, but I'm going to use my calculator just to make sure. It is, it's 0.04. And then we multiply that times 0.10, which is going to make it 0.004. So 300 is equal to K times 0.004. Because if we simplify all of that math, it comes out to 0.004. So then I can divide both sides by 0.004. And I'm going to get a really, really gigantic number for this. But that's okay. This is science. Sometimes you get huge numbers. So the answer that I got was 75,000, or 7.5 times 10 to the 4th power. So now let's think about the units K is going to have. Again, if I look at the units on the rates that were given to me in this experiment, it's in units of molarity over seconds. So I know that molarity over seconds is equal to K times a molarity held to the 1st power, and then multiplied by a molarity held to the 2nd power. So let's really think about this. We're going to have to end up with molarity over seconds. What we've got is molarity times molarity times molarity again. So we've got molarity cubed. We're going to have to multiply that by something to end up with just a single molarity on top and seconds on the bottom. So let's think about what we could multiply that by. We need to get rid of 2 of the molarities on top, so I'm going to put molarity squared on the bottom. That way 2 of those molarities disappear from the top. I'm also going to put seconds on the bottom because I need it for my rate. And then since nothing has to go on top, I'm just going to put a 1 there. So our unit for K is going to be 1 over molarity squared times seconds. I know it's a really weird unit, and I know that this process is very strange, but that's how you guys need to determine the unit for K. It's going to end up being whatever unit is necessary to end up with your correct rate unit for the experiment. And also I want to point this out. The rate constant is a lowercase k. We're going to be dealing with an uppercase K later. It's important to realize that when you see a lowercase k, we're dealing with a rate constant. Okay, so let's talk about the order of a reactant versus the order of the reaction, overall order of the reaction. So each reactant has an order that was determined from data. Right, in the last experiment, we figured out that it was first order, it had an exponent of 1 with respect to reactant A, and then it was second order, had an exponent of 2 for reactant B. It's the sum of those exponents in the rate law that equals the overall order of the reaction. So let me put that. Okay, so the order of the reaction is going to be the sum of those exponents. So for this second example, our order of reaction is going to be equal to the exponent 1 plus the exponent 2, because it was first order, had an exponent of 1 for A, and second order had an exponent of 2 for B. That's going to be 3. So this is third order. So that's actually the easiest part of this, right? Figuring out the order of the reaction, you just add up those exponents. Hope this helps you guys understand differential rate laws and how to use data to determine both the orders of each reactant and the rate constant for the reaction.